between canyon walls, resting beneath oceans, supporting forests, and helping form mountains. Located all around us, minerals are the most common solid materials found on Earth. We depend on minerals and use much more of them than we realize. More than just part of spectacular views, minerals are the basic material, in reality, the foundation for our natural environment on Earth. For minerals serve as the building blocks that rocks are made from. Fragments of minerals make up even the ground we walk on and the soil that farmers cultivate. Indeed, we use minerals every day for many purposes, in ways we're hardly aware of. While learning about minerals in this program, we'll discuss the importance of geology and the earth scientists who work in that field, geologists. We'll look at the different kinds of minerals, consider their characteristics, and learn how to identify them. We'll study gems and discover why they're so valuable. Then, we'll review the minerals known as ores, discuss why they're important, and why it's essential to conserve our mineral resources. First, let's consider the field of geology. Geology is the study of the Earth's surface and interior, and the planet's history. The work of geologists underscores the importance of knowing about the Earth and our environment, so we can appreciate the planet we live on and work to preserve it. Because, in fact, many of our natural resources are being gradually depleted and cannot be replaced. Mineralogy, the study of minerals and other properties, is a branch of geology. Indeed, geologists tell us there are more than 2,000 minerals on Earth, of various shapes, sizes, and colors, as you can see here. Since there are so many minerals on Earth, try and think of some of the ways we use them. Actually, minerals are an important part of our everyday lives, even though most of us don't realize it. From the day we're born, we use a variety of minerals for many purposes. For example, talcum, made from the mineral talc, is a soothing body powder. Gems, like diamonds and emeralds, mark important occasions in our lives, such as engagements and weddings. Silverware makes an impressive table setting for enjoyable meals. And the vehicles we drive and ride in are made of steel, the result of a production process depending on iron. So minerals contribute a great deal to our lifestyle. Let's take a closer look now at the main groups of minerals. First, silicate minerals make up over 90% of the Earth's crust or surface layer. In this group, we find quartz. One of the most common minerals used to form rocks, quartz comes in various colors. Lapis lazuli is another silicate mineral. Feldspars make up a substantial part of the Earth's crust. Topaz, garnet, and zircon are three other members of the silicate mineral family. Next, carbonates are another major group of minerals. Calcite is the most common carbonate mineral. Appearing in many different crystal shapes, calcite always forms six-sided fragments. Among other carbonate minerals are the colorful malachite and rhodochrosite. Rocks like this marble and dolomite are comprised almost entirely of carbonate minerals. Finally, the third main group of minerals are iron-bearing minerals. Not as common as silicate or carbonate minerals, iron-bearing minerals are important economically because they contain the metal iron. Iron is often combined with oxygen or sulfur to form an iron oxide or iron sulfide mineral. Hematite is a widespread iron oxide mineral. Lodestone is also an iron oxide. Highly magnetic, lodestone was used for direction needles on the earliest compasses. Making up the three main groups of minerals, then, are silicate, carbonate, and iron-bearing minerals. Consider this question for a moment. What exactly are minerals? Are they living? Can they be man-made? Can you give a definition? Scientists define a mineral as a naturally occurring, inorganic compound with a definite composition and structure. Complicated? Not really, once we break this definition down to show what all minerals have in common. For instance, consider this. Are these substances minerals? The plastic that this bottle is made of? Or the concrete that makes this building possible? Are these minerals? No. Of course, plastic and concrete are not minerals. But why aren't these substances considered minerals? These substances are not considered minerals because plastic and concrete are made by people. Although they contain minerals, these substances are not found in nature. And as we said in our definition, minerals occur naturally. That is, they develop through nature. Now, how about these substances or products? Why aren't they minerals? This piece of coal, this cotton shirt, or these crackers? Why aren't they minerals? Minerals cannot be made from living things. That's why a mineral is described as being inorganic. These products are made from living things. Even coal is the remains of organic bodies that lived millions of years ago. How about these substances? Why aren't they minerals? The gas that powers vehicles, oil used for heating systems, or the water that makes up so much of the Earth's surface. Ask yourself, why aren't these substances minerals? All minerals must be solid. That's why liquids and gases, like these examples, don't meet our definition. Another point is that minerals have definite chemical compositions. Some minerals are made up of atoms of a single element, like this piece of gold. Others, like this quartz sample, are compounds, that is, made up of two or more elements. In the case of quartz, the two elements are oxygen and silicon. The last characteristic in our definition is that minerals must have a definite structure, similar to the form of a crystal. In other words, the atoms in a mineral are arranged in an orderly pattern that is repeated over and over, like the structure in this building. Notice how the girders form a framework of support for the structure here. In a mineral like this piece of quartz, we can see the crystal pattern. Quartz always forms a six-sided crystal. Remember then, a mineral is a naturally occurring, inorganic compound with a definite composition and structure. So far, we've taken a look at the field of geology and geologists. Now, for review question number 1. Scientists have successfully developed synthetic diamonds. These diamonds look and feel like naturally occurring diamonds. But compared to real diamonds, artificial diamonds are very inexpensive. Why do you think this is? Here's the correct answer for the exercise you've just completed. Naturally occurring diamonds, like other minerals, took millions of years to develop and are in limited supply. Once these minerals are used up, they won't be available to us again, so real diamonds are rare and valuable. We now have a definition for minerals. But with more than 2,000 different minerals on Earth, how can we identify specific minerals? Think for a moment. What suggestions do you have for identifying and naming minerals? To help clarify our thinking, look at the people around you. Each person is unique. What are several features that help describe you and your friends? In describing a person, you might have mentioned height, weight, facial features, and other characteristics. In a similar way, minerals have their own unique characteristics that set them apart from other minerals. Color is the first characteristic that most of us notice about minerals. Here, for instance, the green of the malachite, or with this mineral, the blue of the lapis lazuli. Although color seems a good way to identify minerals, don't be misled, because the color of some minerals, like this quartz, can change due to the presence of other substances known as impurities. For example, here we have quartz made purple by a small amount of iron. And here, quartz that's rose-colored from the inclusion of the element titanium. Also, some minerals are almost the same color, even though they're different. Can you tell the difference between this mineral and this one? This one is pyrite, known as fool's gold. And this one is real gold. Color can also change when a mineral is exposed to the air. Normally shiny silver, for example, becomes dull and tarnished from air exposure. Since a mineral's apparent color is not reliable, we need other ways to identify minerals. The streak test is often used by scientists to determine a mineral's true color. Like rubbing chalk on a blackboard, the streak test scratches a mineral's surface to reveal what's underneath. All you need is an ordinary wall tile. Then, rubbing a mineral against the unglazed tile, the mineral breaks apart. Using the streak test on gold, the gold leaves a gold streak, and pyrite, fool's gold, leaves only a black mark. And the mineral hematite, which may appear red, brown, or even silver, leaves a streak that's always reddish-brown. But some minerals, like this quartz, or gems like diamonds, are so hard they don't turn to powder and leave any streak. Because of this problem, scientists use a scale of hardness, like the one we see here, to identify and evaluate minerals. Developed by a German mineralogist named Friedrich Mohs, the scale has become a standard for geologists. Mohs' scale of hardness rates minerals on whether they can scratch other minerals or be scratched themselves. Everyday objects like a fingernail, copper penny, and steel file are shown for comparison. On this scale, 1 is very soft, and 10 is very hard. What is the hardest mineral shown here? A diamond, with a rating of 10, is the hardest mineral here. What is the softest? Talc, with a rating of 1, is the softest mineral and can be easily scratched by a fingernail. Cleavage is another test for identifying minerals. Cleavage refers to a mineral's tendency to split along flat surfaces, as in the case of this mica, which comes apart easily, always splitting in the same direction. Thus, geologists describe mica as having one good cleavage, while other minerals like feldspar, which splits 2 ways, have 2 good cleavages. Some minerals split 3 or even 4 ways. When minerals don't break along cleavage surfaces, geologists say they have fracture and break unevenly, like this piece of quartz. For identifying minerals, then, there are several reliable tests, including the streak test, the scale of hardness, and the cleavage test. As we noted earlier, minerals serve many practical purposes, making our lives more efficient and comfortable in numerous ways. Here are some more examples. The mineral sulfur makes possible fertilizer and matches. The accuracy of superior timepieces often results from precise quartz movements like this. And glass and pottery also contain quartz. Calcite is found in toothpaste, graphite in pencils, gypsum in chalk, and halite in table salt. To be sure, then, much of our modern lifestyle depends on various minerals. But perhaps no other mineral is so sought after as gold. The basis for trade and commerce for centuries, gold, when it's discovered, has excited passions and provoked massive mining efforts. Gold rushes, like those in Brazil, California, and South Africa, have, through the years, made adventurers seek their fortunes in rugged natural environments like the western United States, Australia, or Canada's Klondike region. Deposits of gold in the form of veins are often eroded by weather, with the mineral's heavy gold flakes washed into stream beds or valleys, where prospectors search for them. Gold, besides its commercial value, is often used in jewelry. Not only beautiful, but soft and easy to work with, gold is a favorite mineral of craftspeople and artists. From the earliest recorded time, valuable minerals, unequally distributed on the Earth's surface, have created problems between nations. Disagreements over such minerals as gold, silver, iron, and diamonds have resulted in tensions, sometimes leading to war. For example, the discovery of gold in South Africa in the late 19th century helped cause the South African or Boer War. So some minerals have not only a practical value for each of us, but a strategic importance for nations. Well-formed crystals are minerals considered semi-precious by geologists and the general public. As we mentioned earlier, minerals have a recurring pattern with a crystal appearance. Quartz forms perhaps the most impressive crystals, with the most eye-catching of these minerals often found in geodes. Geodes are cavities in rocks that were once burning hot. There are many varieties of quartz in various colors, such as smoky quartz, amethyst, and agate. There are more than 2,000 kinds of minerals on Earth, divided into 3 main groups, which can be identified by such means as the streak test and hardness scale. Ranging from talc and sulfur to gold and quartz, minerals have both practical and decorative purposes. Gems, however, are undoubtedly the most famous and visually impressive minerals. Beautiful in appearance, rare and extremely hard, the most valuable gems include diamonds like this, emeralds, rubies, and sapphires. Comprised entirely of the mineral carbon, diamonds are found in deep, narrow veins in the earth. Geologists believe diamonds are formed more than 100 miles beneath the Earth's crust, under crushing pressure and intense heat. Later, diamonds are carried closer to the Earth's surface by volcanic eruptions. Pale green and six-sided, emeralds are made of the mineral beryl, with the best examples coming from South America. Rubies and sapphires contain the mineral corundum. Rubies are blood red, while sapphires are a rich, transparent blue. Metallic minerals play an essential part in all of our lives, since they are the source of our most important metals, which make possible many of the modern advantages we enjoy. Various minerals contain such metallic elements as iron, copper, aluminum, and lead. Often attached to other substances, these elements must be chemically separated to be used. Geologists call such minerals ores if they contain enough of a metallic element to make extracting them from the earth practical and profitable. For example, the two minerals here, limonite and hematite, are good sources of iron. Chalcocite and chalcopyrite are among the minerals with copper. The mineral galena contains substantial amounts of lead. And bauxite is the principal ore for aluminum. Metals derived from these ores are used in many ways. Iron, probably our most important metal, is the basis for steel, making possible various structures, machines, and appliances. Electrical wiring utilizes copper. We find aluminum in cans and lightweight structural materials. And the uses of lead include storage batteries. Obviously, our lifestyle depends on the availability of minerals and ores. But mineral resources are non-renewable. Once used, they do not replenish themselves and cannot be replaced. Scientists predict that if the present rate of high consumption continues in the United States and elsewhere, some mineral reserves could be exhausted within the next 100 years. According to these experts, the United States has less than 10% of the world's population, but takes more than 40% of the mineral resources used on Earth each year. Think for a moment. How can we make better use of our mineral resources and not be wasteful? Scientists stress that we can make better use of our minerals by conserving our resources and recycling the materials we do use. Geologists point out we must make every effort possible to preserve the natural environment when we remove mineral resources from the Earth's surface. Minerals are often removed through tunnels from underground mines, but open pit mines are also used for iron and copper. Such surface mining sometimes results in land erosion and toxic runoffs. In such instances, ecologists urge a policy of land reclamation with provisions for replacing topsoil and replanting vegetation. In this program, then, we've discussed the importance of geology and the earth scientists who work in that field, geologists. We've studied the most important minerals and learned how to identify them. We've taken a look at gems, seen why they're so alluring and valuable. And then, finally, we've reviewed the metallic minerals known as ores. Above all, we've discovered that minerals provide the physical foundation for life on Earth, and that only through understanding these resources can we use them intelligently and preserve this planet's natural environment.